The title of today's topic is a simple 3D renderer done in 100% in LabVIEW. And thanks for attending, and let's see where we get to. So as is tradition, we're going to start with our giants of female. And the eagle-eyed amongst you will notice on the middle line there is actually my mom's name. So this presentation is dedicated to my mom, who unfortunately passed away a few weeks ago. She had a fight with cancer, which she was victorious with, and then unfortunately she succumbed to Alzheimer's 2 weeks ago. And my mom was an incredible lady, but not technically minded. You know, on the right we bought her this Joker calculator for Christmas one day, and the amazing thing was her inspiration to me in using technology. Her and my dad saved up money to buy our first computer, which was a Commodore 64, and that got me really into computing. And then they later on bought me a 286. And my mom never nagged me when I spent too long on it. She never kicked me out and told me to go play outside. She just let me be. I think she could see how much joy it was bringing me. And without that, I'm not sure where I would be today. So, Mom, thank you for everything. You're an amazing woman. And yep, this is dedicated to you. Thank you. You've made me who I am today. So I don't want to spend too long on that slide, otherwise I'm going to end up crying. So let's move on to something else. A little bit about me. Again, I don't think anyone's super interested, so I'm going to go quite quickly here. I currently work at Philips in Eindhoven in the Netherlands, where I'm part of the test and verification team. And we implement, design and implement test equipment for some of the large medical technology equipment that Philips makes. So CT scanners, MRI machines, all sorts of things. I started my journey with LabVIEW 6 way back in 2003 or 2004. So I'm approaching 20 years. And along the way, I've kind of collected a few accolades. So champion, instructor, and a few other things. But this presentation is not really about me. It's about LabVIEW and 3D. I mentioned at the beginning, oh goodness, there's somebody at the door. Good thing today's a school day. My kids are home. Let's see if they can deal with a stranger at the door. I'm just going to pause a bit while I listen to the interaction. Okay, the door's open and closed. I guess my kids have dealt just fine with somebody at the door. I do love it in the Netherlands. I feel completely safe for my kids to open the door and to talk to some random person. Oh, I've got a package. This is not scripted, I promise you. Do you want to say hello? Okay, thank you. I think I ordered some toothbrushes. There they go. Thanks, Alexis. Okay, sorry about that. I'm doing this presentation a little bit backwards. As I mentioned, I have heaps of content, and I don't want to skip out some of the good bits. So I'm doing some of the thanks and links right at the beginning. All of this code is available on my GitHub. You can check it out there, neilpate/3D engine. But more importantly, hit the link below that, which is the LabVIEW Discord server, which you might not know about. Quite recently put it together. It's a friendly place where we can talk all things LabVIEW. The QR code should work, or there's an invite link. Both of those should hopefully work. If they don't, just message me afterwards. And again, I said I'm going to start with some thanks. I've definitely left some people out of the slide. Don't presume this is everyone, but I've been super fortunate enough to be part of the LabVIEW community, which is just such an incredible community. Everyone's so friendly. Everyone shares their knowledge, their time. You know, it's all volunteer based. We have such a fantastic community. So for everyone on this slide, and for those who are not, but who know they should be, thank you so much for your inspiration and your help and helping me be a better LabVIEW developer. You're all amazing. Thank you. Now, let's set some expectations. This is a software 3D renderer done in LabVIEW. You're not going to get Unreal Engine 5, which is what you're looking at in the background there, which is pushing something like 1 billion triangles and multiple textures. You're not going to get that. You're going to get something a little bit more like this. So this is a screenshot from a one of the productions done by a Demoscene, a group called Renaissance in 1992. These guys were absolutely my inspiration growing up in South Africa. I'm not sure how I got a copy, but one of these things made it onto my computer. And for those who don't know, productions are basically tech demos where people show off their coding skills. And the phenomenal thing is that this was running on a 286. So you're getting like 30 frames a second, 3D rendered, potentially textured graphics with sound on a 12 megahertz processor. I could only dream to one day be as good at coding as these guys. But that's what you're going to get, something more like this. One last thing. When learning about 3D, there's just heaps of tutorials out there. There's almost too much content. One person I did stumble upon is One Lone Coder on YouTube. He's this British guy who's got a really, really approachable way of teaching. He doesn't treat you like an idiot, but at the same time, he talks you through concepts which you may not be familiar with. So go check out his YouTube channel. He's got some really good content, and he implemented a 3D renderer on the console. So I've kind of taken some of his maths, which was C and C++ based, and turned it into LabVIEW code and then just run with it. Okay, that's it. That's all the slides we have time for. Let's actually jump into some demonstrations. Okay, I just got to share my screen again. Okay, perfect. Hopefully you can all see my desktop. I have LabVIEW open. And again, if you can follow along at home if you download the code. I'm going to start with the demo. So I'm going to show you pretty much all the features first, and then we can dive into implementations. We can talk about optimizations. We can see where this goes on. But effectively, this is just a toy application, right? There's no design went into this. There was no peer reviews. It was just something that grew out of a fun hobby in the evening. This is not shipping code in any Philips products. This is just something that I've knocked together. So we have a main VI, which obviously I can run. This is all LabVIEW code, so it's running from source. And there we go. So I promised you it was some kind of 3D rendering engine, and it's clearly doing something. It doesn't look very 3D. I get that. Right now we have a square. So there's a square. Squares only has 2 dimensions last time I checked. But in fact, I'm just kind of messing with you. This is actually a 3D scene. So if I click on the square, I can then rotate it, and hopefully that's viewable. And you can see some kind of cube that's being rendered on the screen. In fact, that's a bit too far away, so let's bring it forward a bit. So here we have a pretty simple model with 8 vertices. So the cube has 4 vertices on the top, 4 vertices on the bottom, and we're basically just drawing it in 3D space. Now, the important thing to know is 3D maths is hard, but it's not super hard. It's really just a bunch of well-known formulas that have been established for several decades. What makes it hard is you implement something and then you forget about it. And when you go back and look at your code, it kind of makes no sense because it's just a bunch of sines and cosines and some random matrix maths. And that's all 3D is. Or typically modern 3D, which is quite obviously not done in software anymore. What I'm showing you is completely software rendered. Modern 3D is all done on special hardware and GPUs, but the principles are pretty similar. To take any point or vertex and to do something with it, you typically represent it as a point in 3D space, and then you apply a bunch of matrix multiplications. The maths kind of is pretty clever. If you take a 2-dimensional matrix with size of 4 by 4, then you can represent almost any, I believe it is, any kind of transformation that you would want. So using just some maths, you can do things like moving an object around a scene, rotating it around an axis. And you can do all of these things quite efficiently by chaining together matrix multiplications. And that's all it is. And the nice thing is that this is all parallelizable. Oh, gosh, I'm surprised I got that word right first time. So modern GPUs are so good at that because they can just do these manipulations in parallel. Our 3D renderer here is just a pretty primitive single-threaded software implementation, but effectively the principles are quite similar. Okay, I'm just going to refer to some notes because I've got a lot to show and I don't want to skip anything out. Okay, so here we have a cube, and it was one of my goals to make this fast. I wanted to have a 3D renderer which felt really nice and fast, and I was aiming for something like 60 frames a second. So one of the first things I did was implement some kind of frame rate counter. So you'll see at the top, press H to toggle help. If I press P, I get some stats. So I'm going to turn the help back off and press P. So you'll see here the frame rate I'm getting is about 120 FPS. And in fact, it's typically about 140 for the scene, but I'm losing about 20 FPS just by sharing the video on Hopin. So Hopin's really eating quite a bit of my CPU. But what we can see is some number of visible triangles being rendered in a certain period of time. So in fact, where are the triangles? You can't easily see them, but you can picture each face split into triangles. In fact, to make it a little bit easier, I implemented a line mode where I can draw some lines. So you can now see the triangles are represented on the screen with the lines. It's still a bit complicated because you can't really see because of the filled triangles. So if I press T, I can turn off the triangles. So here you can see now what makes up a 3D object, or at least this cube. We have 8 vertices, so 4 on the top, 4 on the bottom, and connected together in some kind of order to form faces. And that's all you need to do. Every object in 3D can pretty much be split into triangles, or sometimes they use quads, but let's just pretend it's triangles. And if you want more detail, you just need more triangles. And you can add more and more and more triangles to get more detail. Obviously, the more triangles you add, the more the software has to do. The more mathematics it has to do. Every vertex has to be calculated every frame multiple times, depending on where it's moved, where it's shifted around in the scene. You see at this point, my frame rate is about 120, and that's mostly being taken care of or effectively constrained by the presentation time. And in LabVIEW, sorry, I don't have the block diagram open. I should have opened it first. So my screen is just a 2D picture control, so in LabVIEW. And unfortunately, this is quite a slow beast. To do anything with this is just quite slow, and I'm spending most of my time just drawing pixels on that. So for this simple scene, all the time has been drawn in presentation. So let's bring our scene back on, rotate it a bit. So yeah, you can see the nice thing about 3D is it relies a lot. You can debug a lot using your intuition. I can, as I moved there, you may have seen something weird happen there. I can clearly see I've got some kind of bug in my implementation. It's drawing one of the triangles above another one. But you just get a feeling for things. There's some complicated maths, but you can very easily tell if the maths is working or not. You could just look at something. When I spin this and I rotate it around the y-axis, and just a bit of nomenclature, in 3D, there's lots of different sort of coordinate systems that you can use. Left hand, right hand, Z up, Y up, all sorts of things. The one we're using is the same that is used by Unity, and in fact was used by this one-line coder. The axis up and down is Y, so positive goes up. In this direction is X, so positive X. So you can think of the screen as a typical XY plane, as you would look on a piece of paper. And then your depth dimension is Z. And we have Z going into the screen, which in fact is a left-handed coordinate system. So if you put your hands out and you do that, then you've got X, Y, and Z is pointing into the screen. The opposite obviously is a right-hand system where the Z is, the axes are just flipped. The math is basically the same, but some of the signs are flipped. Okay, let's change the scene a bit. It's kind of boring with just this cube. Let's throw a few more things onto it. So in our project, I have a scene class. Again, this is not heavily loaded with classes. I know 3D Math sometimes is. You can have classes which draw themselves. We're not doing anything like that. This is pretty much the only class we have, and it's really just a convenience class to keep a whole bunch of data in the same place. That's sort of how I write OO these days, is simple classes like that. So I have an initialize VI where I have disabled a few things just so that I can add them later. So I'm going to add a bit more to the scene. So I'll show you if I rerun it now. Now we've got a bit more. We've got some kind of floor, and we've got this bright green teapot. And this is actually kind of a famous teapot. It's called the Utah teapot. I believe it's from the mid 70s or something, when 3D was just first starting and computer scientists and researchers were getting into it. Some guy decided to model a teapot that he found at home. So this is actually a commercial teapot, and it had the nice property of symmetry around the y-axis. So I think this guy used some kind of positioning device, and he manually effectively modeled it. He got the coordinates, and then he entered it into some file, and he wrote a paper, and other scientists wanted to recreate his results, so they got his model, and he shared his model online. Well, not online. I guess back in the 70s there would have been some other kind of technique, DARPA or the original university networks. But anyway, so this is a model, and in fact, if I bring up my statistics, you'll see now we're rendering a lot more. So we had 12 visible triangles previously, and now we've gone all the way up to 7,000. So there's a lot more going on. And we also have our floor, which is a 20 by 20 matrix of these little flat squares. And we're still getting quite a good frame rate. You know, it's not the 60 I wanted, but it's pretty good for now. So here we have our teapot. And again, we can do things like move it around, move it back in the scene. And again, I talked about intuition. You can see I'm moving it further into the screen, and the object's getting smaller. And that's what we kind of expect. We live in a 3D world. We interact with it all the time. We're used to perspective mapping. So things that are farther away get smaller. Now, in the 3D engine, none of that's coded in. You know, there's no special magic saying that if an object's further away, I need to scale it. I need to make it smaller, or I need to. It's just the way the maths works out. In that when you're doing a projection from where the camera is, and obviously a camera is sitting over here and we're looking into the screen, objects that are further away naturally end up getting smaller. So again, it's really intuition, and that's what makes it really fun. Again, you can see I'm moving it in the XZ plane. So remember, that's X and that's Z. So I move it on the XZ plane, you can see the teapot stays on the floor. So again, intuition feels that this is just working correctly. So let's look at a few more features. Performance is always key, right? I said I was aiming for 60 FPS, and one of the 3D is a lot of tricks, right? People do a lot of tricks to make a scene look the same, but actually, there's just tricks involved. And one of the simple tricks that they can do, it's kind of obvious, is if I have an object and I'm looking at it, well, there's things that I can't see. So there's all the vertices on the back of this teapot, which are present, but actually I can't see them because I'm looking from the front. But I'm still currently drawing them. And if I move around the scene, and that's one thing I didn't show you, if I can move my camera around. So if I turn my camera and I look from the side, then I can see the back of the teapot. So it's shaded a bit badly because of where the light is positioned, but you can see the back of the teapot. But in fact, there's a trick which is almost always used, which is called backface culling, which is where effectively you turn off the objects that you can't see, or the vertices. You don't bother drawing them. So if I come back to the front, and there's a bug in my implementation, but it's a kind of cool bug because it allows me to demo something. If I press B, you'll notice two things. First of all, the number of visible triangles really dropped quite dramatically. So it went from 7,000 to 4,000, and my frame rate went quite high. You'll see it gone from 60 down to something like 48, with not too much visibly noticeable in the scene. You can't actually see it. You'll see a little bit around the back there, but typically it's visually mostly the same. So this is with backface culling disabled. And if I press B again, backface culling is turned on because my frame rate's higher. But now let's take a look at the teapot from the side. So if I pan my camera again, if I turn, you'll see I'm only drawing half the teapot. I'm only drawing the half as though the camera was looking from the front. So that's actually the bug in my code, in that my backface culling algorithm doesn't take into account the fact that the camera can move. But it's kind of cool. I left it in there on purpose because it's a really nice demonstration of the backface culling in action. So let's see what happens if we spin it. So I can select an object and I can turn on my turntable. And in fact, I can spin the teapot and you'll see that pretty much all the faces on the back side are being removed. So if I was looking at it from the front, it still would look good. Let's go back and actually look at it from the front. Sorry, my keyboard controls are a little bit primitive. So there we go. So from the front, it looks correct. You know, I'm only drawing the bits that I actually care about. But from the back, it's all hidden. So, and that gave me a nice performance boost. And you've got to keep these optimizations in mind all the time. You know, 3D scene very quickly gets too slow. You know, as you draw more and more triangles, and you've got to render them, draw the pixels for them. Even on a modern CPU, if you're doing this bit by bit, it can get quite slow quite quickly. And you know, I guess the pinnacle of 3D software rendering sort of happened in the late 90s, where we had games like Unreal and those kind of things, or some CAD programs. And from that point on, people moved to hardware acceleration because it's just clearly was better. Okay, so you might see something else weird going on with my cubes on the side here, and that some of them are not being drawn. These ones on the corner here and this here. But as I move my camera out, they do get drawn. And what's happening there is effectively I'm clipping to my screen space. So I have a picture control, which is 800 by 600 pixels. That's just something I've hard-coded in software. And clearly, as I move the camera in and out, objects become larger and smaller. And at some point, they effectively move past the camera. And they move past the camera, and in fact, then they really start getting big sometimes. Now, there's two things. There's no point drawing something that's behind me. There's also no point drawing something that falls out of the width of my picture control, the 800 by 600. So I've implemented a really primitive algorithm just to say, well, if an object falls outside, don't bother drawing it, which is why you'll see that the triangles, it's not the actual object itself, it's the particular triangle is not being rendered for the ones that go off the side of the screen. Right. Okay. You may have noticed that we've got, oopsie, yes, there's the turntable. I need to turn that off. We've clearly got some kind of lighting effect going on. You know, as I rotate my cube, the color of the cube is actually constant. It's this diffuse color, which is sort of the overall color of the material. And as you rotate it, clearly faces start to get lit, and then they become dark, and then they get light again. So there's some kind of simple lighting model that's been implemented. And it's a bit more obvious on the teapot. Well, not more obvious, it's obviously different because there are way more vertices. We can change the color of objects. So if I select something, I can then change it, and in real time change the diffuse color. Let's pick something here. Here's a nice green that I found. We'll call this NI green, shall we? And it's kind of cool. So this was actually a bit of a LabVIEW trick that I found just purely by accident, in that the color updates while the widget is still open, and I'll show you how that's actually possible later. But purely by chance, there seems to be, I would almost call it a bug in LabVIEW, but I'm quite happy with the bug because I quite like this effect of being able to show the color as it's moving. So let's talk about the light. And in order to do that, I actually want to turn on my light source. So although the light is present, I can't do anything with it. So let's go back to our initialization method. And at the end here, I have a light source. And all the light source is a representation of the light in my scene. Now, I have to apologize. This is a little bit confusing the way I've implemented it. It kind of looks like the light is coming from here, and that's not correct. What you need to imagine, in fact, if I select it and move it around, so you see the light is clearly changing. So if I look at my teapot, let's put my teapot somewhere more in the middle. If I take my light and I can actually bring my light around. So I can move my light around, and you can see the light is moving. But what's actually happening is this is a point, and the light direction is from this point to the origin. So the light beams are parallel, they're covering the whole scene at once, and they're covering from this point in space. So if I put the light up, then effectively it's shining almost straight down. If I put it over here, it's shining from this to the origin. So that's the important thing. It's shining in that direction. It's not actually coming from there, because if I move the light somewhere else, you see this face is still being illuminated because the direction of the light is in this. It's just a vector. So effectively the whole scene is illuminated by light parallel rays in that. So even over here. So this is bad. I shouldn't draw it like this. I should draw it as some kind of vector showing you the light direction. And in fact, in programs like Unity and I guess Unreal, they don't model it like this. They show you parallel rays with the direction. That's what I should do. But I figure it's still kind of cool. You know, again, intuition shows you that this is sort of working. I can move my light around. I can move it, in fact, under the objects. And things start to get dark. I can move around, and it just kind of feels really cool. Like that's half the problem with 3D is once you get started and once you've got past the 3D maths, you just start adding features because it's really just fun. It's so much fun to do. And in fact, that's why I don't have any slides, because I spent most of my time just playing around with the software. I'm just taking a look at the comments. Yeah, so there's a comment here about directional lights versus spotlighting. That's exactly right. What I've implemented is a directional light where the direction is pointing in some direction towards the origin. Typically in things you have the addition of having a spotlight where it's genuinely coming from that, and you define a cone and intensity. But my lighting model is quite simple. I've kept it just at that. Okay, keeping an eye on time. Let's just put my light back here because there's a further few things I want to show you. Again, the eagle-eyed may have noticed there's a few things I haven't touched here, and that's alpha blending and an alpha slider. And now alpha is just transparency. So let's play around a bit with this. I'm going to take this cube, I'm going to put it down over here, and you can see that naturally, that's one thing I didn't demonstrate, is as I move the objects around, they naturally clip through each other, and that just happens because of the maths. You know, I'm not implementing any kind of clipping algorithm. It's just that the order in which the things get rendered. But let's put something like this here, and so clearly the cube is not visible. But now I'm going to turn on alpha blending, and you'll see I can slowly make my teapot transparent, and it disappears till eventually it's no longer present. So what's actually happening there is when I draw it to screen, the pixels themselves, I look at the previous pixel that's been done. One thing I haven't touched upon is how we obtain something to be in front of something else. And we use a really simple algorithm called the painter's algorithm, which is where we sort the objects of the scene and we just draw the furthest away ones first. So start with the ones far at the back, kind of like a painter would do, draw those first, and eventually you finish with the ones closest to front. And what effectively happens is that your frontmost objects are at the front. But that allows us to do this sort of alpha blending, because when I'm drawing my pixel, the further away objects have already been drawn, and then I can actually sample it and look to see the value and kind of do some blending of some value of my diffuse color proportionally. The one thing I should note though is if I turn the statistics on, you'll see my frame rates drop massively. So my alpha blending algorithm is totally primitive. It's really not efficient. I just threw it together, just for fun, and it kind of works, and it's on my to-do list to make it a bit faster. And yeah, I'll get around to it one day when I finish doing the fun stuff. But you can see it's clearly doing something, you know, from an alpha of 0 all the way up to an alpha of 1. And again, apologies if I mixed up terms. Maybe that's 1 and 0. I'm an electronic engineer. I actually have no formal training with any kind of 3D stuff. This is all just self-taught and everything. So when I use terms like rastering and Painter's algorithm and Utah teapot, it's just things I've picked up. Okay, so let's. I'm going to turn the alpha blending off because the frame rate's really rubbish like that. But let's put a few more things into the scene. My frame rate's really bad right now because my cube had alpha blending turned on. So let's add some more 3D to the scene. So at runtime, I'm actually going to import a model, and I found some models on the internet. These are some open source models I found. So this is a spaceship. So it's a bit blocky. I'm actually going to turn this teapot off because it's killing my performance. So here's a nice model I found of a spaceship with some blocks. It's like a voxel one. And you can see there's heaps of triangles now. It's 27,000 triangles. And it's still doing a pretty respectable 15 FPS, and it's lit. You know, I can move my lighting source around, and it's not the best implementation, but you can see it all clearly just works. And that's the nice thing, is once you've got the basics working, it kind of scales quite nicely. I'm using a really simple 3D object format called OBJ, which is a open source standard. It's really old. I think it's probably from the 80s or 90s when 3D software was being developed and they needed open formats. Effectively, it just it just lists the vectors, it just lists the vertices and the faces. Let me show you what a file looks like. If we go back to our no, I don't know what those are. So here's our cube, and the cube basically consists of 8 vertices, so where it's V, so vertex 1 through 8, at some position in space. So X, Y, and Z. So my cube is two units across every dimension. So it's 2. And then we have some faces where you just take the index of these vertices, and these are effectively your triangles. So your faces are your triangles. And this just scales arbitrarily. You can have my teapot has 10,000 items in it. It has heaps of vertices and heaps of faces. But the nice thing is once you've written importer, and I'll show you what that looks like in LabVIEW. So that is a typical object file. V's are vertices, F's are faces. So again, just purely primitive way of doing it. Just scan from string, make up a bunch of points, and that's it. That's my 3D object. And from that point on, I treat objects as collections of triangles. And when I do the maths, I just do the maths on all the triangles. I'm hoping we're going to get time to go into that. So yeah, that's pretty much all the features I wanted to show you. I wanted to leave some time into actually looking at some of the code. So let's do that now. Let's talk about the actual implementation. So again, I repeat, I wanted to make this simple. I really wanted to, if the implementation wasn't simple, I got rid of it. And certainly I went through some few iterations developing this where I tried things like having multiple loops and using DVRs for the buffers and all kinds of crazy things. And I pretty much scrapped almost all of them because they were a bit too complicated for not really any value back. So at its heart, we have a really simple while loop with a case structure, or an event structure with a timeout of 0. So this happens all the time, effectively meaning that our update VI is running as quickly as it can. So the update is, this is what is on the main cluster here. The cluster has our scene, our 3D scene, and then the pixel buffer. So this is our 2D array of pixels, which we draw to the screen. And again, I thought about putting this inside here, and I tried various things, and this is what I ended up doing. But I encourage people anyone curious to grab the code of GitHub and try and play around and see if they can make it a bit quicker or see what cool stuff they can do. But effectively, the update routine is just this. So we have this a bit busy, but effectively you have two things going on. We update our pixel buffer. So that's all the maths, that's all the transformations. And then we draw it to the screen, which is we turn it from pixels into a 2D picture control. And you'll probably notice that these guys run in parallel. Effectively, what I did to improve performance is I pipelined this. So on one frame, we update the pixel buffer, we store it, and on the next frame, we draw the previous frame. Just because I don't really care if I'm one frame behind, if it means I almost double my frame rate. You know, this thing here is losing 5 to 10 milliseconds of performance. So if I'm one frame out, I don't really care. So that's kind of one simple little optimization. Because in fact, if I look at the picture control stuff, so again, I'm digging in a bit here, just going from pixels to picture control is really slow. So LabVIEW's picture control is not amazing. I mean, it's quite old technology. It's not really designed to do this kind of thing. But taking an 800 by 600 matrix and turning it into a picture takes about 5 milliseconds on my PC. Now, I don't have a super fast laptop, but you know, this just takes the time. And clearly, makes no difference what the scene is. This is just pixels at this point, or it's a 2D array. But even there's room for improvement. And in fact, a lot of the picture control stuff, some of it's open source. So if you dig inside, you get something. And if you dig deep enough into some of this code, and again, this is shipping code with LabVIEW, it turns out that actually the image is not a 2D array, it's a 1D array, where some sort of reshaping is done. So I strongly suspect that if I cared enough, I could figure out what the format of this 1D array is and throw away all this maths and kind of hand roll my own. And instead of having a 2D array, you know, as if those of you who caught James's presentation yesterday, there isn't really such a thing as a 2D array in memory anyway. It's just a 1D array that's treated slightly differently. But some optimizations may work better than others. So that's one area where I could improve things. Another few places, sorry, sometimes I get a bit lost. You know what LabVIEW's like with all the windows. But while I'm here, let me talk about a few little measurement tips and tricks I did. You may notice this delta time, which is being used to benchmark. And that's one thing we have to do. You know, 3D is complicated. Things happen a lot, and I want to measure it as accurate as I can. So I took some inspiration from the shipping Vim in LabVIEW, which is stall data flow, which is this thing, where in fact we have a wait inline, but I changed it slightly to the high resolution timer. So in fact, doing this, I can do a little bit of maths, and I can, because it's a Vim and it's inlined, it's really quite nice. I get the data type, and I can drop this guy down wherever I want to measure between this point and this point. And I do this all over. So the presentation time measured pretty accurately, and I can use it to measure things. And you'll find this all throughout the code. And the good news is this actually happens quite quickly. This is only some tens of nanoseconds to iterate or to run that bit of code. So this itself isn't slowing the code down. That's some of the problem sometimes is you put things into measure, but the things you put in actually end up slowing your code down, and you sometimes draw the wrong conclusions. I know at one point I was using the profiler. So I was using this performance in memory, and turning on the profiling made the program run 10 times slower. So it kind of defeated the point, because I was trying to see which things took the longest. So I was trying to optimize the hot paths. But in fact, doing that made me draw some of the wrong conclusions. So it wasn't super useful. Okay, so let me just get rid of, yeah, okay, this code's still runnable. Some other things that are worth optimizing is if you're dealing with picture control stuff, when you draw text on a screen, you need a bounding box or this cluster here. And in fact, it's really slow to figure this out. So we can't actually, this is locked. I don't know what's going inside here, but I guess it's using the font, and it's figuring out how big the bounding box should be based on the font and the text. And it's really quite slow. And the fact is that it doesn't change that often. So I've just got a little bit of maths in here to check, well, actually only every 100 frames bother recalculating the value, otherwise use it. And it's just for my statistics, for my box on the screen, so no one's going to notice if it's out by a little bit. So it's just one of those sort of practical speed ups that I'm put in place. Okay. Sorry, LabVIEW, you know what it's like. Let's take a quick look at the update routine itself. So this is where we do all the maths. So effectively, I have one VI. Again, you know what it's like with LabVIEW. These are all the objects in the scene. Objects consist of triangles, and this is effectively the main maths loop. So there's a bunch of matrix multiplications which happen in here. So if we want to rotate anything, sorry, I'm kind of rushing because I'm running out of time, but this is an example. If you want to rotate an object by 90 degrees, then if you apply this 4x4 matrix to a vector, it will actually effectively rotate it. And it's just basically a bunch of sines and cosines in the right place. So here's some C code that I borrowed from the OneAlone coder and re-implemented in LabVIEW. I really love the way you can just paste stuff on the block diagram. You know, it's so useful to be able to refer to things like this. And you saw earlier in my object importer where I had a picture of the Blender screenshots, I had a picture of my Notepad++, and I just love that feature about LabVIEW. So matrix maths, effectively, we just do a whole bunch of math. So a triangle itself consists of 3 points. Points get multiplied by rotations. You then translate them, and these are all just some multiplications to get a transformed triangle out. I do some illumination. I project it. I do my blending. I don't want to go too much more into this because it's the 3D math is complicated, and I'm not going to do it justice if I rush too far through it. One thing I would like to point out is some of the benchmarking that I did. So not in there. I've got to find it. So I did just some brief statistical analysis to see if I was getting the same frame rates as when I ran my application. So this is the full scene, and I'm running it 1,000 times just to see. And typically I'm getting a kind of a normal-ish distribution, which is what I would expect. But the nice thing is that now I can debug my code sort of in here without having to run my complete application. Benchmarking is hard. You know, it's very easy to draw the wrong conclusion from your benchmarking. In fact, I have some line drawing algorithms. So one thing I've completely skipped over is how to draw a triangle. So at its heart, we talked about how things get drawn on the screen, and everything's triangles. So you can see here if I move things around, this is my triangle, and to draw a triangle, it's quite well known. You just split it into 2 halves. You get an upper half and a lower triangle, and then effectively, and this is the cool bit that I completely glossed over, is all you need to do is draw horizontal lines. So I can fill my triangle by drawing a horizontal line, which is a row in memory. And as James mentioned yesterday, its LabVIEW is row major, so the rows are contiguous in memory. And it's really high performance. And in fact, I did some benchmarking with some of the help of people on Lava on how to draw. Sorry, some of this code gets a bit messy as we dig in because it's a bit complicated. But effectively, split the triangle into 2, draw an upper triangle, draw a lower triangle, and that's it. You have a full triangle. Sorry, the code is getting messy at this point. But there's one thing I want to show you. And at its heart, this is the VI that's been called over and over and over, which is draw a horizontal line. So this is really the hot part in the program, because it's being called for every single triangle, for every single row of that triangle. just being called thousands, tens of thousands of times per second, if not hundreds of thousands of times, perhaps more. So I implemented different techniques to see which is quickest, and I stumbled upon some really cool stuff. You might not have seen this before in LabVIEW, and that's to use MoveBlock. So I know we say LabVIEW's data flow and there's no pointers. But that's not entirely true. I can impact this array by using a MoveBlock with the pointer. So I can actually update this using this the DLL call. It's a method call in LabVIEW itself. And when we did our benchmarking, this was the quickest technique by some margin. It was probably twice as fast as the most naive trick, which is just iterate over a 2D array, and in fact, this is just a 1D array, but do it pixel by pixel. So this is sort of the super naive way of filling a line, is just figuring out where your line starts and stops and drawing each of the pixels. This is quicker, MoveBlock. And we did some benchmarking. We thought, right, this is going to be the quickest. And then I ran it in my scene, and it was actually slower. And it took a bit of head scratching. But what I'd done when I benchmarked is I'd assumed the worst case of filling in the whole line of the whole width of my screen. And it is quicker when your line is longer. But typically in my scene, my lines are actually smaller. So I guess the overhead of all of this stuff was actually more than if I just did it element by element, which is quite quick. And I guess it's at some point it's a trade-off between, well, not a trade-off, but the one technique starts to dominate over the other. So I could potentially start to mix and match these two techniques. Yeah, I've got 10 minutes to go. I could spend another hour just talking about all the maths and things like that. How about I see there's any questions or anything that I've missed that we'd like to go through? I see some comments about the different kinds of shading, some Weber. Absolutely right. You know, there's just so much to this. You know, the 3D's been around for kind of 30, 40 years now. And to recreate it all would take one person a lifetime. But the nice thing is it's kind of fun. So after a long day of work, kids have gone to bed, nice cup of tea or coffee or something, it's sort of fun just to get involved in. Let me see if there's any questions that I've missed. Phoebe, you mentioned double buffering. We do actually kind of do double buffering in effectively the update loop itself is double buffered because we've got it pipelined. Essentially, this is double buffering. We're pipelining one frame while we're doing the rest. So it effectively, you can see here a copy is being made. That is effectively double buffered. And if you look back at my Git history, you'll find different implementations of the buffering, double and triple, or flipping and doing all sorts of things. But eventually I settled for this because it was simple enough to reason about and high performance. David, do I have any older versions of LabVIEW on GitHub? I don't, but I don't think there's too many dependencies. I could probably back save this up to the point where the Vims stop working, which I guess is 2019. Okay, let's stop it there. Okay, sorry, Mohammed says a question. How show the color box? Yes, okay, great. Sorry, thank you for reminding me. So just to remind you what happens if I run the scene and I pick an object and rotate it, I can update the color in real time. And what's actually happening there, purely by a quirk that I stumbled upon, if you read the value property, effectively it's being updated while the widget is open. So if I go into my update, so purely by chance, this value on the wire is actually updated in real time, even though this thing here would not be. So this wasn't being updated, but the value property node was for some strange reason. So they actually were slightly different, but happily for us, this did what we wanted to. So in real time, this value was changing. So by doing that, I was able to keep the widget open and also update the color. Sure how you got the color box. Yeah, so I do actually have to select it. So I've got some kind of ray casting algorithm where I click in my scene and I see what object I interact with, and that becomes my active object. There's a whole bunch of housekeeping I haven't shown you guys to track which objects are active, and I've got things name-based lookup and proper data types. I really did gloss over a lot of things. Uh, Jürgen, did I make that myself? I'm not sure which bit you mean. Yeah, I made everything myself. The mouse selecting, that's done completely by myself. Effectively, we have on the mouse down, I can select the object by almost the same as drawing it. I just draw it and then I see which, oh goodness, sorry, it's gone into the wrong screen. I see which object I've collided with, and in fact, then I can use this built-in VI to see if the point is within the polygon. So this code's not super performant, but it only happens when I click, which is pretty rarely. What is the future? The future is really how much time I get to play with this. I've got this really dumb idea that I want to implement hardware acceleration, but I want to do it myself using LabVIEW FPGA. I saw some presentations before. I think Pascal did a great one of Doom on either a serial or an FPGA. I would like to implement some of the rasterizing or the hardware transformer lighting on an FPGA, and then use a LabVIEW software application to hand over the data to the FPGA to get it to do the heavy lifting. That's one thing I'd like to do. Unfortunately, on my laptop, I don't actually have space to put a FPGA card in. That's one of the problems. I might need to get a PC or some kind of Serio. Also, I'm not convinced that the overhead of all the calls will make it any quicker, but that could be kind of fun. And then there's heaps of other stuff. If I look at my to-do list, I want to implement anti-aliasing in the scene. So in the 2D scene, there's some pretty fast, relatively simple techniques to get rid of some jaggies, by sampling neighborhood pixels and comparing colors. So I think anti-aliasing could be quite nice. But the big one for me actually that I really want to do is texture mapping. So at the moment you saw all the objects were flat shaded, and in fact I'd like to have some kind of texture projection onto them. So that's something else. And the trouble is, you could just keep on coming up with ideas. I went out for a jog last night and I thought, well, why don't I hook up my object to a 3D a DAC and I can show a signal in real time. The ideas come in quicker than you can implement them. So this will probably keep me going for several years. Okay, great. That's it. I'm going to hang around for a bit more. Thank you all for attending and listening to me drone on about LabVIEW and 3D. There's heaps I've left out today, but yeah, do yourself a favor. If you're interested, go grab the project, run with it, fork it, do whatever you like with it. If you've got any improvements, please send them back in so we can make it faster. And it can be a fun little project. So great. Thank you all so much.